presentation, and please, you can start.
Thank you very much, Anna, and thank you everybody for inviting me. Thank you to the organizers. The most difficult part has already been achieved, which is basically sharing the screen on an iPad with the idea that I should be able to scribble this, which is some people find very annoying, some other people find very interesting and useful. But anyway, I hope that the talk itself is not going to be too peripheral to your interests. There's a little bit about conceptual modeling, but most of it is on how you can optimize re-execution of data pipelines that are expensive to run, and they must be run more than once. So there's basically three more parts or three more key messages. One is basically we're talking about data evolution and the impact that it has on data-driven processes. Then I would like to touch upon the PROV1 provenance model. And for those of you who are familiar with PROV, which is a W3C standard for modeling provenance, this is a slight extension of PROV, which is used as part of this ReComp project. And then I'd like to conclude with an outlook on ReComp. ReComp has finished its job, or better say, has finished the money. The job is not finished, and we're looking for collaborations on doing exciting extensions in various directions. I hope to have a little time left to talk about that. Okay, this is my standard intro slide, which basically says, oh, there's a big analytics machine that takes big data on one side and then produces magically actionable knowledge. And what is interesting is that all of the ingredients that are in the picture evolve over time. We are going to focus specifically on the top part, which is basically the meta knowledge that goes into the analytics machine, and that consists of libraries, tools, and algorithms. For example, if it's a number of algorithms in genomics that the people here would be familiar with, we are going to specifically refer to, talk about reference data sets. This is, after all, a data-centric kind of project. Okay, so the very simple setup is really almost trivially, but just to set the scene, you have a function with n inputs and m outputs, and every time you compute f on x, you get a result. And what we're going to do is basically map the abstraction on essentially workflows that can be black box workflows or workflows that we can inspect the structure of. So in this case, you have a couple of inputs, one output, and a couple of data dependencies. So let's pack the data dependencies for a second and focus on what happens when the inputs change, just to fix ideas. So if you have any change of any element of any of the inputs, then you basically have two main options. One trivially is react to the change and refresh everything every time. And it's obviously that's not what we want to do, because it can be inefficient, effective, expensive. But most importantly, you have to balance that against the benefit of re-executing every time. And there are many circumstances where the change in X is small enough that it doesn't actually warrant a change, a recomputation, because the difference in the outputs will be negligible. And if you can measure the benefit associated with this difference, then you can start thinking in terms of something slightly smarter to do. Okay. Just incidentally, the other thing that is very fashionable to do these days is approximate f with some function of prime that is a lot cheaper than f to compute, and then every time you can afford to compute f prime on every new version of x, you're not going to get an exact result, but you get something that's close enough to survive another day. Okay, so what we do is basically take a third approach, which we call a refresh if needed. And this assumes that you can actually measure the distance between two data points, either X or Y, and in this case, y. And if you do that, so basically if you have a metric on the Y space, then you can try and estimate the difference between the old output and the new output without actually computing a new output. And that's kind of the whole game. And then if you can do that, and then trivially say, okay, I set a threshold, which is going to be application specific, user specific, and then decide that it's worth to actually compute the actual f of x prime only if that difference estimate is large enough. So when does this work? It works when obviously you have well-defined spaces on X and Y where your data points live, and that is not a given. And we'll give an example where this is actually not so straightforward. And also when F is stable in a mathematical sense, explained here. So basically, every time you have a small perturbation on X, you have a correspondingly small perturbation on Y. And so you can hope to basically use this distance here to estimate the distance here. So without having to compute this element here, you will come to some reasonable conclusion that by estimating epsilon y, then you can apply your threshold and off you go. Okay, so I would like to give an example of this setup, just to show that it's actually not as simple as that. Okay, and so we drop into genomics, which hopefully is the domain that you are familiar with. And so I'm not going to comment much on these pictures. They're both taken from the Broad Institute kind of brochure style of the variant calling standard variant calling best practices pipeline. All it says here is that it is complex. It takes a long time to run on any given exome, at least to our estimates or in our implementation. And the problem is that it's actually not particularly stable because a number of the elements in this pipeline can change over time. So because this is a very heavy weight pipeline, we actually have focused on a follow-up process, which is down here. It's basically once you have your variants, let's say 40,000 variants which are in your exome, and then you have a disease hypothesis. For example, the hypothesis that I want to confirm is that you have Alzheimer or some other neurodegenerative disease, for example. Then what this very simple process does is consult a couple of reference databases. This is OMIM, GenMap, and ClinVar for variants. And come up with an annotation of the variants and a filtering of the variants that are pertinent to the particular phenotype. Okay, so this will be, if these are 30,000 variants, these would probably be, 200 variants or something like that. And they're annotated with either benign, pathogenic, or I don't know, which is often the case. Okay, so the problem here is that the function is not stable in the sense that we have explained earlier, because small input perturbations can have a devastating effect, as you probably know. Okay, so and that's because one single bad variant can be responsible for a particular genetic disease, although not all diseases work that way. Well, then what you do is come up with some heuristics. And in this case, if you have observed change in the set of variants, because you have basically redone the variant analysis or variant calling on an exome, then you can come up with simple heuristic and say, okay, I can either, if the changes in the phenotypes, I suspect it's not Alzheimer's, it's something else, then there's nothing to do, you basically refresh. But if you change in the patient's variants, then when you have new variants, then you have a monotonicity kind of property, which says basically the ones that you had are still bad news if they were bad news yesterday. And so all you have to do is run SVI on the new variants on. Okay, so this is not rocket science, and this is not super interesting because basically, namely the GMAP database and ClinVar database change much more often than that. So ClinVar changes every day, in fact, and GMAP every month, something like that. And so now you actually have this function which now has these dependencies. So we want to focus on the dependencies for a couple of reasons. So the first is that because they change more frequently. The second is that the changes can be substantial. I don't know if you can read this, but basically between 2012 2014, there has been a spike in the number of variants associated with a particular disease. This is for a specific phenotype, and this is across all phenotypes that were considered in the experiment that we did a few years ago. Okay, and for another example, I'll just borrow a slide that Anna Narif kindly gave it to me, which I only partially understand, but this is a good chance for me to introduce ViruSurf, which is the group's latest basically warehouse database of virus data. And again, you have basically a time-dependent variability in the frequency of variants observed within that data warehouse. Okay, so I'll come back to ViruSurf hopefully towards the end. Okay, and there are reasons why this changed and are listed here, because new knowledge, because the variants are recomputed, and there's more sequences submitted to the labs and so forth. So all these interesting changes. Okay, so given that these changes happen, how do we account for them, and what do they really mean? And again, we're going back to SVI, this simple variant interpretation workflow, and I say, okay, well, this is just a relational table, and trivially, my difference is just set difference. What's complicated about that? So if you can see the colors, just this really trivial set difference will highlight that you now have a plus, so added and removed. So these are added pathogenic variants for a particular version of ClinVar, and actually some variants are actually being retracted because these things happen, and others have been updated in the clinical significance. Okay, so when this happens, then you would like to react to these changes. And again, you can come up with some heuristics. So, for example, you can say, well, red variants are the pathogenic ones. Okay, and these ones, well, actually, so the red variants are removed. So there's an inconsistency. Let's call red variants the bad ones, and amber variants the I don't know, and then green variants actually the benign ones. So any variant that is now in ClinVar moved to red causes a high impact, but only within the subpopulation of my within my analysis population that is affected by the variant. Okay, so now when I talk about dependencies, I have one more degree of freedom, which is or more dimension, which is across the population that I've analyzed so far. So if 100,000 people, only 10 have Alzheimer, then basically that's my scope. If the change in ClinVar has one variant that's turned red, which we know it's an Alzheimer variant, okay? And we know that because we can consult GMAP for that, okay? So basically we come up with a bunch of variants here. When the variant changes status, it becomes benign or becomes deleterious, then you check whether it's in scope. And if it's in scope, you already have the results from the previous execution of your workflow on patient X. And all you have to do is a very simple, inexpensive operation. This is which of the variants actually are in this output, and I update If I have a brand new variant, then I recompute SVI on all inputs because, and that can be expensive if it is an expensive process. It just so happens that this process is very, very inexpensive. It's essentially a bunch of queries, but we use it for testing and proof of concept. Scrolling down here, okay. Okay, so as I said, what is interesting here is now we have a further dimension, which basically not all cases are affected. And you can come up with heuristics, again, that says, okay, obviously, if a variant V is pretty much what it says at the top, really. A variant V is within the scope for a patient X, if X has a phenotype which somehow is compatible with what we know about variant V. Okay, so if we can perform this operation cheaply, then we can clearly isolate the population within scope, and the rest is inexpensive. Okay, so I just wanted to draw home this point, because it is actually one of the interesting things about ReComp is that most of the input functions, and I'll talk about input in a second, are of this nature. This is good news and bad news. The good news is that you can find them if you have enough expertise in domain. The bad news is that they're very specific to the case, and so they don't lend themselves well to generalization. Okay, so let me try and make that point. So first of all, SVI is, as I said, is an unstable function. One red variant can change your diagnosis. Yesterday you were good, today you get a disaster on diagnosis. And so these are the black dots here. Okay, so here you have versions of CleanVar, as you can see, monthly for a year. And on the columns you have a population, which is broken down into three phenotypes. They're all neurodegenerative diseases. And these are actually real data from our Institute of Genetic Medicine from a few years ago. The game here is to hit the black dots without actually recomputing the entire matrix, and so without recomputing a whole row every time. Okay, so if you assume that you have a cost associated with each of these dots, you would like to compute the black ones, so predict which ones will be black without touching the others. And the others, incidentally, are these ones. Actually, there are changes, but they're not going to change your diagnosis. You're still good, or you're still in, tough luck. The dots are nothing changes at all, and there's these small ones that actually retracted variants that actually bring back your diagnosis to something better than it was a month before. Okay, so because we have this sparsity issue, we have implemented these heuristics and kind of shown that this refresh if needed approach works in this case. Here is a brief summary. It is probably not exactly the same set of versions, because this is 1 year later. Okay, so it's not exactly the same matrix, but the idea is that now you've been reducing from a whole 500 executions to about 70 runs by trying to predicting. And because you can be conservative or aggressive in your estimates, then in this case, 71 is more than what you should have done, which was 14, but you have no false negatives. Okay, so the moral of the story at this point is that you have we have a framework that allows you to plug in this heuristics that tries to estimate the impact of changes in input on the previous output. Okay, and this is summarized in this slide. This is a bit of LaTeX again. So now you have the X where the dependencies are now made explicit, where small d is a current state of some data source D, and you can look at changes in D, and you can look at changes in X, and you can have all these combinations of executions, same D, different X, and so on. But now you want to have a data diff function for the data dependencies, which is in the case that I've shown is very simply like set difference. In reality, I glossed over a number of details, because it's not just that you have added the record, but you have added the record with just certain characteristics in the label. Basically changes the label, the status of the variables. So you have to be a little clever here, but it's still very straightforward. Okay, and so if that is the case, then what we do is define in a general formulation. We have an impact of a change from D to D prime to versions of the database on a single input X, which is basically measured as the difference between the results obtained using by computing F on D and D prime. And the game is to actually estimate the impact without computing F of XD, and actually F of D prime here, okay, when F is not stable. So, and this is basically the ReComp function. Okay, the ReComp function is something that encapsulate your logic for estimating the impact given the difference in the inputs, well, a difference in dependencies and the old output. And let's say it's just binary for simplicity. So what you have is a notion of a scope, which is a set of all the elements of the population which are affected by this impact. Okay. So far so good. As I said, this is interesting because we have several case studies where interesting impact functions exist, but they're really hard to generalize. So what we're looking at now is a different dimension. We're looking inside the structure of the process itself that implements F. Okay, as I said, think of it as a workflow, and it can be a black box like this. And we now I've now introduced input function and delta function for difference. So you put different functions associated with some of the inputs and output. Input function, yes, associated with one or more of the outputs. Okay. So now basically we're translating everything that we said so far in the setting of a workflow computation, and we actually hope that the workflow looks something like this rather than black box. That gives us more freedom to play around with different functions. For example, I may be able to differentiate two versions of GMAP, but in this example, and actually on CleanVar here. Okay, but for example, I don't have a different function of the phenotype hypothesis or for the input patient variance. That's just the way this example goes. I could actually have deltas here as well. So, okay, so and I have correspondingly input function that may actually try to measure the output, the impact on partial output, as well as impact on the overall output of the process. So at this point, the game becomes more interesting because the more I know about this process, and the more I can inspect the structure, the more granular I can try and be in defining my input functions as dependence on the. You can see like this input function depends only on CleanVar, and these only depends on GMAP. So I basically separated two sets of heuristics because I have this white box structure. Okay. Now, if I can do this, then the next level is okay. If I now every time I run one of these workflows on a particular set of inputs with a particular version of the dependencies, I start recording the history of each execution, then I can afford hopefully to do some more granular optimizations. And this is an example. Okay, I can basically, I would like to automatically compute this red part of the workflow, which corresponds to changes in CleanVar, and the blue part is actually not affected by changes in CleanVar, and vice versa for GMAP. Okay, and if I do that, then I have a boundary, and at the boundary, if I keep track of the if I cache essentially intermediate results here, then I can do things like partial rerun, for example, which optimizes the execution when the corresponding instance is in scope. Okay, so now I have a scope. I decided patient X is in scope, and now I can run this analysis that says how much of the workflow for patient X do I actually need to rerun. And the beauty of this is that actually because the structure of the workflow is the same for all patients, the impact might not be the same, but the structure is the same. Then if I run this analysis on the structure of the shared workflow, then basically I have a way to optimize all of the workflow instances that are in scope. Okay, please shout if you have questions and so forth. Okay, so let me speed up a little bit because time flies. Enter provenance. Okay, I can't ideally, please raise your hand if you know about PROV, but let's pretend you don't know about PROV. PROV is a data model for modeling the provenance of data. Is generic enough to accommodate essentially provenance of anything, and this is like the core of it. Okay, it's standardized by the W3C a few years ago. So there are entities, think of them as data, activities, think of them of blocks in a workflow or functions that consume and produce data, and agents, which are essentially, in this case, whoever is responsible for the data, whoever is responsible for running the workflow. Okay. So a bit more closely, you have this part here, which is the entity agent activity core. And then what we added, I say we because I was part of the consortium, is this idea of association that says, okay, there's an agent which is otherwise unspecified, which is responsible for executing a particular function on a particular piece of data. Okay. So this is where Prov stops, and I urge you to, or invite you to look up the specs. The URL is very simple right here. There's a whole family of specs here. What we did in the context of a project called Data One, an NSF project in the States with other colleagues, is extended this in something that we call Prov One, because it was done with Data One. Okay, that's kind of, yeah, the joke. And here is a little sketch of what we've done. Okay, so basically the top part is kind of core Prov, and the bottom part is an expansion of what an agent might look like when an agent is actually a workflow, a process. Well, basically, when the agent responsible for running is described as a workflow itself. Okay, so here you can basically have a workflow, which is a particular type of program, and program can have subprograms. So I have nested workflows. So I have nesting here. And what is important here, I have ports. Basically, each program with a block in a workflow will have an input-output ports, and ports will connect it to each other through channels. This is derived from a couple of types of workflow structure that we were familiar with when it was Kepler, and one is Taverna, which I used in my previous research. Okay, so so much for UML. Actually, what is interesting is now there is a connection here. There's a big interface here between the runtime, which is what happens at execution time, and the static structure, okay, of the, excuse me, I can't write on glass. I don't know about you, but I never get used to it. So the execution time provenance says, okay, a piece of data has been used. The structure will say, well, this piece of data was actually observed on a port, which is a port of a particular block. Okay, so I'm connecting what I observe at runtime with the structure that I'm aware of. And it comes out something like this. Okay, so at the top, I have my structure. And I have a workflow with 3 blocks. There's no nesting, but there could be sub workflows here. And I actually have on the left here some notation, which is like a prolog, datalog-like notation to say the things that describe the things formally that are in here. Okay, that basically describe the structure of the workflow, the ports, input-output port, and the static connections. Okay, and then in the bottom part here, you have the runtime, which is what I observe when an instance runs. And I then make a connection. I say, well, the B3 execution is actually an execution of a block B3, B1 execution of block B1. And because I have I2 is an input port to B3 and O2 is an output port of B1, I can actually say that data D, which was used by B3, was actually observed on input port I2, and it actually comes from output port O2 of B1. Okay, if you're not confused enough, then they should probably make sense. Just keep in mind that basically there's a static structure and there's a runtime counterpart, and they map to each other quite nicely. And so this is the syntax for the runtime. Okay, so this association here really describes the interface between the 2 parts. Okay, so besides, if you leave syntax aside, what you can say, basically build a narrative out of this formal syntax here, which you can read here. So I have which part of which I've read already. Okay. So why is it important? Okay, now I'm gonna brutally fast forward to how we use this workflow provenance structure by skipping essentially all the details involved in how we do it. But essentially, this is what a real workflow looks like when it implements a function like SVI. This is eScience Central, which is a homegrown workflow from our group. And it consists of actually sub workflows. So there's a master workflow, which is what you see. And then there is a sub workflow, which you see here, which expands. And as part of it, there's another sub workflow here that expands and so forth. Okay, so if you you have a horizontal dimension, which is how data flows horizontally through the workflow, but now we also have an invocation of essentially subroutines, you can think of them as sub workflows. Okay, and so now leaving all the details aside, because I don't have time to go into this, there are references at the bottom of the slides. What we can achieve by having enough granular provenance described using Prov1 is that we can now play the game of selectively recompute fragments of this complex workflow which are affected by a change. And again, details are in various papers at the end of the presentation. Okay, so so let me zoom out again and kind of summarize what ReComp looks like. ReComp is essentially now a meta process. So it takes a process and it does two things. It observes what it does, which by looking at logs, provenance, whatever is available to observe the process in action. And if it's a white box structure, we can afford to describe it fully with Prov1. And everything goes, for every execution, goes into a history database, which actually happens to be a Prolog database. Some old school people in the room might be happy to hear, which then runs a number of interesting queries, and all the selective recomputation logic is essentially implemented as Prolog queries. Wonderful. Okay, so that's the observing bit. And then there is when do you trigger ReComp? When changes occur. Okay, when change events occur, then well, we said that we need data diff, the deltas on various inputs, some, not all. So we need to be able to quantify the changes. If we can do that, then we have some hope to measure the impact, so estimate the impact of changes, as I said at the very beginning. That defines the scope of what needs to be rerun. And then we go into this game of selecting relevant sub-processes or sub-workflows and ignore the rest. So there's two-level optimization here. And then if you're really, really lucky, then you have a workflow management system that actually allows us to do partial rerun and the game is complete. So that's kind of the ideal theoretical best case scenario. And it's not always like that. We have a couple of good case studies where we show that some of it is possible and some of it, when it's a black box, not all of it is possible. Okay. So now, given this ReComp meta process, we can put it in context. And what I thought I would do at the end of this talk, and I think we have a few minutes left, is zoom out again. Okay, so that's ReComp, and as I said, it does two things: observe and control a process. Okay, if you now put the context around the process, then you can have, for example, an interesting data warehouse that feeds the process. That's an ideal situation. Why? Because, well, as I said, you want to diff every time there's a change in the inputs, but not all change might be relevant. So the example that I gave on SVI being a relational table, and I just do a relational set difference, it's a very trivial one. I may not be interested in everything. In fact, I may only be able interested in Alzheimer or other conditions. And this may not be as simple as clean variant, can be a complex data warehouse. And this is where this is where the work that the group at Politecnico has been doing comes into scope. And we had a few exchanges, and I'm going to show hopefully a couple of slides that they kindly provided to me. One concern a query language that looks at that basically allows sophisticated queries on a particular type of data warehouse, and I'll look at it in the next slide. But also, I can look at this as a process. It's a data integration process, and this data integration process may be expensive, and it may not necessary to run the whole data integration again every time I have, every time I have a delta on one of the inputs here, especially if the delta is limited. Okay, so I think I hope you get this idea of extending the scope of ReComp to include integration processes and complex queries that may occur on the integrated data set, which then inform the process. And so now I have two additional questions for ReComp to answer. So when should I rerun a query as opposed to a workflow? And which data changes should I react to? So basically, can I use queries on these? Can I use, for example, this query language to define a scope for the changes I'm interested in? Okay, this is a slide about the geometric query language, and I think I only have time to point you to the bioinformatics paper here, and I'm sure that Anna and Arif and Stefano will be happy to talk to you about this. And this is a couple of example of queries that are actually expensive to compute, and for which the group has found interesting rules or heuristics that kind of corresponds to the ones that I gave you at the very beginning. Which basically says, for example, the computation of this particular query.
For example, the linkage of data cloud.
Have I listened to my own voice in a different pitch?
Contributed by researchers and public institutions, but also major companies.
I think there's two people talking here.
Could you please mute all your...
I don't mind, but it may be confusing for some people. Anyway, we're nearly done. There's probably a signal that I should stop talking. But so the first example is, this is a heuristic, okay? If I can estimate that 10% at least of the samples would obtain a changed count, then it's worth running this query, which is a time-consuming query. Okay, so that kind of gives me comfort that the picture that I showed you in the previous slide actually makes sense. And there's another example here where it's even more complex. I'm not even trying to attempt to describe this one, except again the bottom and the right here. The bit at the bottom right here is basically I only need to recompute if I can estimate a considerable change in the peaks found in a particular cell line, and so on and so forth. Okay, so with that, what I wanted to say is that ReComp is alive. I think it's a nice playground to experiment with ideas that tie in with the complex query execution. And with that, I'd like to leave you with a summary, which I'm not going to read through. So I'm going to leave it here and a couple of references. And I think we may have time for a couple of questions. I hope I haven't abused people's time. So thank you very much for listening, and I'm here for questions. Thank you.
Thank you very much, Paolo. Very, very interesting presentation. Also ambitious goals. And let me say that is very relevant to CMLS, to the scope of the workshop. Indeed, we are already receiving some comments. I was expecting these from Oscar and Anna. Also, we are going to have a paper presentation, which is the first in the second session, which I think is very linked to your work, and probably there is some space for collaboration and connection. So I will read Oscar's comment unless he wants to repeat it.
Yeah, I can read it. I have it here. It's basically, it's okay. Data evolution is fine, but how about concept evolution? Wow. Yes. should conceptual modeling based approach be used as a key artifact for a correct data interpretation that evolves in time? And that is especially relevant in the genomic domain, where concepts are under continuous change and open to the discovery of new knowledge. Yeah, so I think concept evolution now it's evolution at the meta level, and it's been out of scope throughout this project, because we discovered that we had enough on our hands with just data evolution, not to mention evolution of tools, algorithms, and so forth. So if your schema changes, then I think that's what you mean here. Then the question is there any scope for saving anything that you knew, or does it change in concepts reflected in the schema completely invalidate everything you knew? And I think, Anna, frankly, I think you have more experience here because you're doing schema integration, and I think you can actually play a similar game at the meta level, where some schema changes may not have a hard impact and may be considered not irrelevant, but you can live with them for a while, unless they're too drastic. Again, I think it is conceptually, I think the framework will be very similar, but at the meta level. But I need to be convinced through case studies and examples whether there's any notion of stability here associated with changes. I haven't mentioned the other case study, which is simulation. That are in many case simulations, if you change a little bit of the input, then a little bit changes in the output. That's nice and stable. Okay, so there are cases in the ReComp space which are stable, and I gave you one which is challenging, and I suspect that similar principle apply in at the meta level. But I'm looking forward to your presentation, and I'll be here and listen. Okay. Yes, I agree. Let's start the conversation. This is fantastic. And then I have Anna say thanks for okay. Identified other attributes that could also have a high impact for clinical significance. Okay, so when all you look at is variance, our friends in genomics tell us that all you look at is the clinical significance of the variant. However, if you go upstream from the interpretation, then lots of things can change in your exome, by the way the time it's sequenced to what is recorded about your exome. You can if you do other types of analysis like GWAS, for example, then you're trying to combine your genotype with lots of other attributes that express your phenotype. And those can change because it depends where you measure it. Okay, so if you're looking at your genetic propensity to develop a certain disease, and the disease is represented by biomarkers, then the time at which you measure biomarkers matter. Okay, and my blood will be different from tomorrow's blood that I have, and so forth. So all attributes, for example, that go into GWAS, just thinking off the top of my head, might actually be relevant and subject to change. And then I think Stefano has a couple of things. Reactive databases, yes. Yeah, absolutely. So the condition, action, and triggers recomputation that's what we've been trying to do. So much of what is done in SVI is actually automated. So we acquire versions of SVI one after another. We do the diff, and that triggers. And then we trigger the input functions automatically that are associated to changes in ClinVar. And based on that, we compute our estimates and decide ReComp or not ReComp. So part of it is actually automated.
So my feeling is that if I can speak, then if we
Sure.
take a GMQL program, it should be possible to syntactically understand what this kind of, let's say, deltas and so on, and come up with a generation, automatic generation of when or what should be done. Maybe not when, but what.
Yeah. So if you look at SQL, if SQL is your
GMQL is similar to SQL. That's why I'm thinking.
Yeah. Okay. So if you basically, if you take a query language as essentially your function language, then yes, you have a lot of scope to try and automatically, I guess, identify what could be the triggers for changes. Yeah, that's an interesting, challenging idea. Yes. What is the other? Oh, and then there's a problem of not precise. So 2 kinds of error: the tolerated error in the output and the tolerated error in the program. Yes, that's also true. If you estimate that your if there's error tolerance in the output, then changes in the input for a function that is stable and well behaved might actually produce perturbation in the output which are within the tolerance, and then there's nothing to do. Now I hadn't thought about programs that are not particularly correct. I like to think of them as functions that approximate the real function.
About the programs that do some calling, and then the calling is, let's say, sensitive to situations that are maybe in the context of the program computation. They might not give repeatable results, I think.
Sorry, I need to interrupt